So good afternoon, everybody. Welcome to the Heidelberg Joint Astronomical Colloquium. And this week we are very pleased to welcome Phillip Podsiadlowski, who's going to talk about how stars end their lives. So I will hand over to Fabian Schneider, Philip's host, for the introduction.
Thank you very much, Richard. It is my great pleasure and honor today to introduce Phillip Podsiadlowski to you. So Phillip has done his PhD at MIT, and he earned it in 1989 on the progenitor model of supernova 87A. And since then, he has been doing pioneering work in this particular object. After finishing and graduating at MIT, he moved to Cambridge in the UK, spent a couple of years, almost 5 years there, working, for example, with Martin Rees and other people. He did a short stint at the MPAA in Garching, before returning to the UK, but this time to Oxford. And then he took up a position there as a lecturer. And in 2006, he was promoted to full professor. And he has been at Oxford ever since. But in 2020, Phillip gave up his position at Oxford and became an independent scientist. And along his scientific track, of course, he has been receiving many awards, prizes, and interesting things. And I would just like to highlight that he has been, for example, granted the Humboldt Prize Fellowship, which he took to Bonn to establish some connections there. And since this year, he is the Klaus Tschira guest professor at HITS. Phillip is going to be here in Heidelberg till the end of this year. So if you want to get in contact with him, feel free to reach out. Phillip is well known for his work on stellar astrophysics, and in particular, for example, on compact objects, or compact object binaries, on binary star evolution, but also on the progenitors of supernovae and many, many different things. And I'm pretty sure he's going to touch upon a little bit of gravitational wave astronomy today. And with that, I would like to hand over. And Phillip, please tell us about the ends of lives of stars. Thank you.
Yes, thank you, Fabian. Thank you very much for the introduction. And it's a pleasure to be here. I mean, I've been here a few times in the last few years, but this year, since I'm the cherished guest professor, I'm here for the whole 3 months. So, and as Fabian just said, I'll be here till the end of the month, at the end of the year, and back in January. So if you want to see me to discuss some of what I'm talking about today or anything else, please come to see me. Today, I want to talk quite generally about how stars end their lives. Now, for some of you, that might sound like an odd title. Don't we know how stars end their lives? Well, we know a lot from observations, and I think we have a fairly good qualitative understanding of stellar evolution and how it connects to observation. But a lot of this is really coming from the observations. There are still quite big gaps in understanding theoretically certain critical questions. Specifically, one is, how do low and intermediate mass stars actually lose most of their envelopes? And how do massive stars actually explode? Now, in my talk, I will first start giving you a basic stellar evolution introduction. I mean, you will have know most of that, but I will extend it a little bit. And then show you some of the observational constraints and then come to the new topics. All right, so this is a one-page summary of stellar evolution. Now, why is there stellar evolution? Stars like the sun, lose energy from the surface. They radiate energy away. And if the star is supported by thermal pressure, you need an internal energy source. Otherwise, the star is not stable. Now, in stars like the sun, we know that energy source is nuclear burning, but an alternative is also gravitational energy. The alternative to, of course, is thermal support, is that the star becomes permanently stable. And permanently stable, I mean, white dwarfs, neutron stars, or black holes are permanently stable because they are supported by degeneracy pressure. No, black holes not, but the first two are supported by degeneracy pressure, which even at zero temperature provides enough pressure to maintain a star against the gravitational pull. Now, a star like the sun is 4.6 billion years old. In another 4.5 billion years, it will have exhausted its hydrogen in the center, and then hydrogen fusion can no longer provide the energy source. So what will happen? The star will contract, and the energy source initially is just gravitational energy, of which half is radiated away, and the other half heats up the core of the star. Now, the sun becomes degenerate, which makes it more complicated. But if you take a 2 solar mass star, this contraction continues till the center becomes hot enough that the next fusion reactions, in this case helium burning, can start. That occurs at a temperature of around 100 million Kelvin compared to the 50 million Kelvin we have in the center of the sun. And stellar evolution is really an alternation of having burning phases and contraction phases. Now, for low and intermediate mass stars, it actually doesn't go that far, because already after helium core burning, you develop a degenerate carbon-oxygen core, and that essentially terminates the core evolution for these objects. Of course, to have a CO white dwarf, which is only about 1 solar mass, an 8 solar mass star would have to lose 7 solar masses. So the central question here is really, how do these stars eject most of their envelopes, and why? Now, for massive stars, and I'm talking about stars more massive than 11 or 12, these nuclear burning and contraction phases continue. So after helium core burning, you get carbon core burning, neon core burning, and so on, until at some point you have an iron core. Now, iron is the most stable nucleus. So at that point, you can no longer gain any more energy by nuclear fusion or fission. And so the iron core, if it's bigger than the maximum stable mass, the Chandrasekhar mass, it has no choice but to contract. There are various instabilities I will talk about a bit later. It actually collapses, and at some point it can leave a compact remnant, which is a neutron star or black hole. And the central question here is really, what happens at this final point? What is the final fate, and which stars form neutron stars or black holes, and which produce a supernova? So this is nicely summarized in this cartoon that shows sort of the distinction between the low and intermediate mass and the more massive stars. So a star like the sun will become a red giant, at some point eject its envelope, probably connected with the planetary nebula, and leaving a white dwarf, which is about the size of the Earth. And the more massive stars also become giants and may experience a supernova and produce neutron stars or black holes. This is all not to scale. I mean, take the sun, it's 1 solar radius. The sun, at the end of its life, will have a radius that's about 200 times bigger. Similarly, for the large stars may be 10 solar radii, but in the red supergiant phase, it may be a factor of 100 bigger. Also, of course, the color is not right. A large star wouldn't be yellow. So that's the simple picture, which you probably all know. We can understand these different fates quite nicely by looking at the central temperature, Tc, and central density for stars of different masses as they evolve. This is a nice diagram produced by Norbert Langer, which really illustrates the various fates stars experience. So if you look here, these are different masses. Look at a 5 solar mass object. Well, it burns hydrogen and later helium. And at some point, it reaches this layer of non-relativistic electron degeneracy, where now the core is supported by electron degeneracy that's stable. And once you have lost the envelope, the density doesn't change anymore, but it continues cooling. So it just becomes a cool white dwarf. If you look at the 15 solar mass track, shown here as a straight line. In reality, it's not a straight line, so this is a bit simplified. But the point is, you go to higher temperatures and densities, and at some point when you have formed an iron core, you collapse and you possibly form a core collapse supernova. Anyway, let me just move on anyway. There's a small version of this. Right, so once you have an iron core, and if the iron core is bigger than the Chandrasekhar mass, it has to contract. And that releases gravitational energy. And in the process, you start to photodissociate the iron into first alpha particles and later protons and neutrons. So in this final core collapse phase, you actually undo all the nuclear burning that you've done throughout the life of the star. You dissociate the iron back into its simplest elements, protons and neutrons. That's possible because you have enough energy, you have much more energy than the nuclear binding energy. And as Christiane Helling will talk about, Anyway, so you end up with just with collapse. You dissociate the ion and end up with protons and neutrons. And at some point, the densities are high enough that the strong force takes over and stops the collapse. At that point, you have what's called a proto-neutron star, just consisting of neutrons and protons, and has a typical radius of 30 kilometers. Now, so the core has collapsed from about 3,000 kilometers to 30 kilometers. In that process, you release a lot of energy. The total energy that's released is about 10% of the rest mass energy. Now, that's plenty of energy, but most of that energy just escapes in the form of neutrinos. So the big question now is, how do you actually get an explosion? How do you get a supernova? This is all collapse, but the supernova is an explosion of the envelope. And this is a problem that has plagued theorists for many decades. How can you just tap some of that energy, and you don't need much, you need only about 1% of the energy that's in this released rest mass in the envelope to produce a supernova. I will come back to how that works later, but that is the problem, the fundamental problem with supernovae. Any questions at this stage? Of course, you get a neutron star only if you get a successful supernova. If you don't have a successful supernova, the collapse continues and you end up with a black hole. So this is what these two curves, these two lines indicate. But as you can see, there are other lines which are also very interesting. For example, if you look at the 9th solar mass object, that enters also into the relativistic, non-relativistic electron degeneracy regime, but it actually forms an oxygen neon white dwarf. And as the oxygen neon white dwarf continues to grow in mass, its density increases. And at some point, it reaches a density of about 5 times 10 to the 9 grams per cubic centimeter. And at that point, you start electron captures on elements like neon and magnesium. Now, what does that do? Now, I said this is an electron degenerate core, so the electron degeneracy provides the pressure. But if all of a sudden these electrons disappear because they combine with neon and magnesium, that support is lost. And at that point, the star loses its support, and you also get a collapse. So this already happens when you have an oxygen neon core. You don't need an iron core. And if that collapse continues, that's another way of forming a neutron star. Now, whether this is the right outcome is not entirely certain. Indeed, Fritz is working on this with some of his collaborators, and they show that it might actually experience a thermonuclear explosion. But for the purpose of my talk, I assume they form neutron stars. But they're different neutron stars from the neutron stars you form from the classical iron core collapse. There's another region up here where you see 2 gamma goes to positons and electrons. So there's a regime where in the core of a star, this is typically when you have an oxygen core, the conditions are such that you can produce electron-positron pairs. Now, in fact, the electron-positron pairs will be in equilibrium with the photons. But what that means is you take energy out of the core to produce the rest mass, at least the rest mass of the electrons and the positrons. That is also unstable because it takes away energy. And this can also trigger an instability. And in principle, you can collapse all the way to form a black hole. And this is probably what happens to very massive stars, if they exist, like 500 solar masses or more. Now, at the lower mass end, you still are in an oxygen core, so you have oxygen burning, which is explosive under these conditions, and that can actually generate enough oxygen, enough energy to completely disrupt the star. So there is this intermediate regime where this instability, this pair instability, can eject completely disrupt the star. This is referred to as a pair instability supernova. We do not have any clear evidence observationally that this is happening, but it's definitely predicted by theory. So to give you a slightly broader picture of the final fates, I show you this figure. So still the basic distinction between white dwarfs, neutron stars, and black holes. But the white dwarfs can either be carbon-oxygen or oxygen white dwarfs. And it has even hypothesized that in the range around 10 solar masses, you might have other types of white dwarfs. Neutron stars, you can form either by iron core collapse or through this electron capture supernova I just described. The importance of these different formation channels is that you predict different neutron star masses and also different supernova kicks. Neutron stars, when they're born, observationally receive a large kick, and that would be different for the two types. For black holes, the simplest case is if you don't have a successful explosion, that the whole star collapses more or less promptly. And in that case, the whole star collapses and you don't need to have any supernova. So what you would see is actually a massive star disappearing. And there are some candidates for this to have happened. But it's also possible that you have a partially successful supernova. So you have some ejection of the envelope, but then a lot of fallback, and that's referred to as a fallback black hole. In this case, you might still have a supernova, but probably a very faint one, where you can even eject some of the core material. Again, these different types of black hole formation predict different properties, in particular, again, different supernova kicks. And if you're in a binary system, different effects on the companion. I'd just like to point out that from the observations of black hole axial binaries, we have good evidence, really, that both of these occur in nature. And then finally, there's a possibility of no remedy. So that's summary of my talk. Okay, let's look at the observations. This is a nice picture, which I've taken from the Sky Telescope, which is a collection of planetary nebulae. Remember, planetary nebulae are believed to be associated with the final ejection of stars before they become white dwarfs. And indeed, in probably most of these, there is a white dwarf at the center. Not all of them are actually planetary nebulae. Some of them are protoplanetary nebulae. But they're very spectacular. And the thing to notice, of course, is that they are often very asymmetric. This is not relevant for my talk. It's generally believed that these asymmetries, in particular these bipolar planetary nebulae, are formed by binary evolution, not by single stars. Now, the more spherical ones or the elliptical ones, even they may not be fully single. Even they may have perhaps a planet or brown dwarf in a close orbit that distorts the mass ejection. Now, what I want here, there's this planetary nebula, which it was on the picture I gave Richard to announce the talk. So this is a very spectacular HST image of the Cat's Eye Nebula. And you see lots of structures. You see all these bubbles, overlying bubbles. You see some jets. And I think there are even some hard X-rays from this system. This is not part of my talk. That's almost certainly due to some binary action happening very late in the evolution of the star. What I want you to concentrate on is actually these shell-like structures. This is part of my talk, right? You see that before the star went into this final phase where lots of complicated things happen, it actually ejected mass in a fairly spherical way, but in a shell-like fashion, right? These shells, and I will talk about this in a bit more detail later, are believed to be connected with thermal pulses in these asymptotic giant stars. Actually, even going further out, we see this. That's the same nebula. This is a nice image produced by Romano Corradi with the Knot telescope in La Palma. Fortunately, the credits dropped off. Again, you see this HST image at the center, but he now has a much broader view, and you see all this mass ejected even before this shell-like ejection. But you also see that this seems to turn on quite suddenly. So what this tells us, that these stars, as they evolve in the AGB, they start to increase their mass loss rates. And this is now referred to as a superwind, because the mass loss rate probably goes up by many orders of magnitudes. In the general picture, the idea is that you lose mass at the rate of about 10⁻⁴ solar masses per year. So if you have a solar mass of material left, you can lose all of that in 10,000 years. Now, how these superwinds work? Well, the standard theory is that you have an AGB star that's pulsationally unstable, and that somehow brings material to a rate about 3 times bigger than the star, where you can form dust, and then dust-driven radiation pressure on the dust. Radiation pressure on the dust drives the mass loss. So that's the picture. This is another important observational constraint. This is from Kepler et al. A recent mass determination of the distribution of white dwarfs. And if you look at the DA white dwarfs, the most common white dwarfs, see they are very sharply peaked at around 0.6 solar masses. So the question here is really, why do you go into the superwind phase? And also, what determines this characteristic mass of 0.6 solar masses? Okay, now moving on to the supernovae. Supernova, as the name says, is a bright new star. This is one of the most famous examples, which only a few of you will have seen, but some of you will have. This is supernova 1987A, which Fabian already mentioned. It occurred in 1987, and it was the first naked eye supernova since Kepler supernova in 1604. So it was something that has long been awaited for. It's not in our galaxy, it's in the Large Magellanic Cloud, but that's close enough. Now, supernovae like this occur in our galaxy every 50 or 100 years. Of course, there are many galaxies. So this is what a supernova would look like in a different galaxy. It's a different type of supernova, but that doesn't matter. There are 100 billion galaxies, so that means there are a few supernovae somewhere in the universe every second. But for nearby supernova, we know a lot. See this arrow here? It actually points at a star or at a light source before the supernova. So it points at the progenitor. So this is very rare, and the surprise was that this progenitor was actually a blue supergiant. I earlier told you that massive stars become red supergiants and explode. This one exploded as a blue supergiant. So before the supernova, it didn't look very much like a star that was about to explode. But the other importance of the supernova is that the neutrinos from the supernova were observed. A total of 17 neutrinos were observed by 2 detectors. Here's the sequence of the individual neutrinos for the 2 detectors. And it's only about 17 neutrinos, and I'm sure they all have their own names. But this was actually enough to estimate how much energy was released in this collapse. And it was about 3 times 10 to the 53 ergs. Exactly the binding energy I mentioned earlier that is released when you form a neutron star. So what this really confirmed is that these supernovae form from the collapse of a massive star to a neutron star. Something that had actually been already speculated in the 30s. Now that was a great success. And as Fabi mentioned, I've been working on this supernova for 36 years. Many other respects, it was fairly unusual. I already mentioned it was a blue supergiant. A few years later, after the explosion, the Hubble Space Telescope produced this picture. And you see these three overlapping rings. The supernova here is only what you see at the center. That's the supernova ejector. All of this is material that was ejected by the progenitor, and from its dynamical age, that was about 20,000 years ago. And just so that you see what it is, this is actually a reconstruction of the geometry of these three rings, right? So you observe the supernovas at the center of the central ring. You observe from this direction, and then you see this overlap of the two outer rings. Right, that gives you the structure. So again, the question is, why would a star eject suddenly a lot of material and in this very odd way? It has approximate axis symmetry, but it's extremely non-spherical. Now, our resolution of that is, and I think most people these days would agree with that, that actually at that time you had two stars that merged. And as we've shown, and I will not go in any details for now, you can actually then really reproduce the rings very well. This is based on fairly detailed hydrodynamical modeling of the ejection you get associated with the mergers, and it's a very good fit to the observations. It does not only fit the geometry, it also fits the kinematics and even the brightness. Okay. Now moving back to the lower mass stars. Why do low and intermediate mass stars eject their envelopes? Now I believe that has something to do with the stability of big envelopes. Now, if you look just at the energy balance of a star, this gravitational energy, internal energy, and again, this is what you do in the introductory course, you can estimate the gravitational energy as gm²/r, and then the internal energy of the thermal energy is just the average thermal energy times the number of particles. And for a star like the Sun, from the Virial theorem, you get that's -6 gm²/2r. Now, that's negative. Makes sense, because it's a bound object, bound stable object. Now, if you take an extended envelope, so R becomes much bigger, recombination energy also can play a role. And recombination energy, that's the energy that's released when two ions combine. In this case, particularly a proton combines with a proton, and that releases 13.6 electron volts. Now, if you also include that energy, which is positive, and add that to the internal energy, you find that the total energy of envelopes, extended envelopes, can become positive. But if you have an object, an envelope that has a positive energy, that means you don't have to do anything to eject it. So it's extremely unstable. This has actually been known for a long time. This was first pointed out by Ludwig Biermann in 1938. And even though they didn't know the composition of stars very well, he did conclude that large stars, giants or supergiants, were dynamically unstable. Now, this idea was picked up by several people, in particular by Paczynski and Jolkowski in 1968. And Paczynski just postulated that when you have an evolved star, an AGB star, where the binding energy of the envelope is positive, that may be the point when you form the planetary nebula. Now, we have looked at this in 1994, Steinman Hahn, Peter Eggleton. And what we did then is we just calculated AGB stars, and to the point where the binding energy of the envelope was positive. And if you then assume that at that point all the envelope is lost and the rest of the degenerate core becomes the white dwarf mass, you get this distribution. All right, you get this. Sharply peak distribution exactly at 0.6 solar masses. Now, this was exactly where the best white dwarf mass distribution at the time was, which was the dashed curve there. Right, so it's a near perfect agreement, which we were very surprised by. But this is why I believe this is a key for understanding the ejection of envelopes in massive in low and medium stars. Of course, the ejection doesn't take place in a single event. This is probably the time when the superwind phase starts. Now, this idea was, of course, has been examined in the past. Tuckman, Sack, and Burkhardt in the late 70s picked up on that idea, and they did hydrodynamical simulations, and they showed that when the binding energy was positive, you get pulsations, very similar to Myra pulsations, and then every once in a while, every 40 years or so, they got a dynamical ejection event. So every 40 years, they dynamically ejected a part of the envelope. Now, at the time, these calculations were quite hard to do. They were adiabatic calculations. And Fox and Wood criticized this because it doesn't take into account radiative cooling. If you have what you see here is the outer radius. When you have these big radii, these stars cool very efficiently just by radiation. And that takes away energy from the pulsation and can kill it. So they concluded that no ejection should take place when that is taken into account. Now, we looked at this problem again, and this was a student of mine, Matthew Clayton, in Oxford. And he was now doing these calculations with modern 1D hydrodynamical simulations calculations. He was using the MESA stellar evolution code, but using the dynamical version of it, and used fairly standard assumptions, and looked at the mass loss of these AGB stars. Now, how much do you know about AGB stars? Okay. These are stars that have finished helium core burning, so they have a CO core, which is degenerate. Outside the CO core, you have a helium layer, and then you have a big hydrogen envelope. By having both a helium layer and a hydrogen layer, you can have in principle both helium and hydrogen burning in the shell. But because the timescales of these different burning phases are different, that is not stable. So what happens in reality is that you get an alternation. You get an alternation of helium burning and hydrogen burning. I didn't do that. Okay, I need my hands anyway. So how does this work? So consider this is a CO white dwarf. Outside of that, you have a helium shell. And outside of that, you have hydrogen. If you now have hydrogen burning, the hydrogen burning moves out and increases the mass in the helium shell. At some point, the mass in the helium shell becomes big enough that you ignite helium. This is under degenerate conditions, so that burning is unstable, and you get an explosive event. And this explosive event moves the hydrogen shell further out and stops the hydrogen burning. And that's what these figures show. That I can't do with my hands. I did nothing. Anyway, questions. Maybe some questions. Yes.
You mentioned the work with Hahn that's at K.
Yes.
The recombination, and then the peak of 0.65 magically comes out.
Yes.
You came to a surprise. Does it mean there is no simple physical argument?
No, it is surprisingly simple.
Okay.
That's the point. I mean, I would have been not surprised if it had been at a slightly different mass, right? So it's really the binding energy becoming positive is connected with this characteristic core mass. That's not the whole story, though, because it still doesn't tell you how you get rid of the envelope. But I think this is where these, whatever happens, super winds or whatever, starts. And that's what you see in around this planetary nebula I showed you earlier.
So the condition is satisfied as soon as the core reaches.
Yeah, I mean, it depends, of course, on the mass. Also depends on metallicity, by the way, but let's not ignore that. Anyway, if you look at this, no, I want to magnify it. Right, so if you look, for example, here at this, anyway, you see enough. So this shows these thermal pulses in action. So whenever you have these spikes, this rate is a function of time for the last 1.4 million years. And whenever you have a spike, that's when you have these helium shell flashes that expands the envelope, becomes bigger, also becomes more luminous. Then after the helium has been exhausted, it shrinks. Then you start to establish hydrogen burning again, and it expands again. So that gives you these characteristic features, either in radius or luminosity. And that is well understood. But in these extended phases, the star is particularly big, and in terms of the binding energy, is particularly unstable. And so what we have done is started hydrodynamical simulations at various points along these thermal pulse cycles. And this is shown on the right-hand side. So in pulse 7, what you see are two curves. The red curve is actually the mass, which is a flat line, so it's constant. And blue one is the radius, which is also constant, so nothing happens. During pulse 10, you start to see pulsations. Right? These pulsations start to grow and reach a certain limit, but you don't see any ejection. Still in pulse 12, you see these pulsations, which are now becoming more similar to what I showed you earlier in Tuckman et al. Get growing pulsations, but again, there's no ejection. But in phase 14, you see these step-like functions in the red curve, which is the mass. So every couple of decades, you get dynamic ejection phases. So you dynamically eject up to 1/10 of a solar mass. And that continues in pulse 17. And this was for 1.6 solar mass star initially. At the end of pulse 17, that has been reduced to 0.7 solar masses. So we think what that could mean is that you really lose most of that envelope in these pulses, doing these pulses in this way. This is consistent also with the white dwarf mass distribution I showed you before. Now, we do understand how this works. I will not discuss that in detail here, but please come to me afterwards if you're interested. It has to do with the recombination of hydrogen and sometimes helium, which drives these growing pulsations. And whenever hydrogen or helium recombines, it suddenly ejects energy. And every once in a while, that energy is enough to produce a dynamic ejection event. Okay. Now coming back to the massive stars. Those of you who came to Fabian's colloquium half a year ago will have heard some of this already. I showed you this figure before and ended that with saying one of the key questions for many years has been, how do you actually convert part of the neutrinos and drive an explosion? There has been a lot of progress in the last 5 to 10 years. And for the first time, people who do these 3D hydro simulations actually get explosions. And the general model, which is accepted by many people, but not by all, is that what we are seeing are delayed neutrino-driven explosions. Right, so in this picture, you form a proto-neutron star, but matter still accretes. That forms what's called an accretion shock. Neutrinos are produced inside that, mostly from the proto-neutron star, and they mostly escape. But there's a region just behind the accretion shock where some of the neutrinos deposit their energy. And in recent calculations, that is enough to convert this accretion shock into an outgoing shock, which is a supernova. Now, there are still many questions, and it takes a long time. You may have to wait half a second for this to happen, which is a long time because that's about 1,000 dynamical times for the neutron star. But that seems to work. So the idea there is you have this standing accretion shock, and once the threshold has reached for ejecting the outer core and the rest of the star, you get a supernova. And this is now work which Fabian Schneider has started when he was still in Oxford, is continuing now in Heidelberg, using these new results and also using state-of-the-art stellar evolution calculations. We can now start to predict what the final properties of the massive stars are. And for this, we use the MESA stellar evolution code, and for the supernova physics, we use the analytic model, parametric model developed by Bernhard Müller, who is one of the people doing these 3D hydro simulations. But since we can't do too many of these, he has a simple model which we can apply to the pre-supernova structure, which we calculate to predict the fate. And the pre-supernova structure that we can calculate using MESA, and it's often useful to describe the final properties in this diagram using something called the compactness. The compactness is just a measure of the binding energy of the inner core of the star, and is defined in this way by O'Connor and Ott, but it's M over R, so it's really just the gravitational potential at a particular mass coordinate of 2.5 solar masses. It seems a bit arbitrary, and it is, but we find that it actually is probably a good measure to predict the explosion properties of stars. You don't have to use this. You could also use the iron core mass itself, or probably more physically, you could use the central entropy. Anyway, if we do this and calculate stars at the end of the evolution, when they have the iron core starts to collapse, we can calculate the compactness parameter, and it's shown here as a function of the carbon-oxygen mass at the end of core helium burning. And you see this very characteristic feature. On the left-hand side, you see it for solar metallicity. On the right-hand side, you see it at a 10th solar. And you see what I want you to concentrate on is you see this peak in the compactness peak, which is very similar on both sides. Now, just using this as an explodability prediction, we would say that all the objects with low compactness produce successful explosion, and therefore neutron stars. The ones with high produce black holes. So this is interesting because that predicts that around 7 or 8 solar masses in this carbon-oxygen core mass, we predict black holes, and below and above, we predict neutron stars. In fact, we can translate that into mass distributions. And please look at the lower half of it. This is then the mass prediction, distribution of masses we predict at solar metallicity. Just look at the dark orange curve. See, there's this strong peak at around 10 solar masses. And then there's a gap, and then you get black holes of higher masses. The most massive at solar metallicity we predict is about 20 solar masses, which is consistent with the most massive black hole, stellar mass black hole we know in the galaxy, which is Cygnus X1. At lower metallicity, it looks actually quite similar. We have the same peak at 10. Then there's a similar gap. And then beyond that, we get black holes. And of course, at lower metallicity, you can get much more massive black holes just because you have less stellar wind mass loss. But the lower end feature is the same. And it's pretty universal, at least based on this theory. This is something we can directly compare now to observations, because now we have LIGO. LIGO, measures the gravitational mergers of compact objects. This shows the gravitational wave signal for the last 1/10 of a second for the spiral in of 2 neutron stars. And you see it's a frequency of about 1,000 hertz. The frequency becomes shorter and the frequency becomes higher and higher, and the signal increases, and that is called a chirp. In fact, I do have this here. Can actually make this audible acoustically. If one just converts that into an acoustic signal, you hear this. Okay, you can't hear it. Sorry. Anyway, it's a characteristic signal. And the important is that the frequency of that signal depends essentially on the combination of the masses, and that's called a chirp mass. The definition of this chirp mass is that this product of the 2 masses. If the masses are the same, it's about 0.9 times the mass of each object. So just determining that chirp, you can determine something called the chirp mass, and that's almost unobservable. And this is what the chirp mass distribution looked like after 03. Ignore the thick curves, just look at the fine ones. These are the chirp mass distributions for almost 100 black hole mergers. So each of these curves gives you the probability for a chirp mass for an individual event. And there are, I don't know how many there are, almost 100. The thing you should notice, first, there are many at fairly high chirp masses, implying fairly massive black holes. And the reason for that is simply that LIGO is more sensitive to the more massive objects. So that's just a selection effect. What I'm more interested in is the lower end. And what you see there as an accumulation of sources around 9 solar masses, and then there's a gap. And then you start to see sources again. And that, at least in the qualitative sense, is exactly what this predicts. So one could argue that the LIGO observations already provide some evidence for this picture. Of course, we only see in the lower mass, and so it's only a small number of sources, so we obviously need much better statistics. But the good thing is, of course, we are getting that. We are now in LIGO started running again, so we are now in the 4th science run. And I checked this morning, they have so far detected 63 more compact mergers, all but 2 of which are likely black hole mergers, which is what we are most interested in. I don't know what their chirp masses are, but it's clear that within a year or few, this picture will either be proven right or wrong. And yeah, we are quite excited about that. And that's where I want to stop.
Thank you very much, Philip. Questions, please. Just round at the back.
Thank you, Philip, for the talk. And I have a question about these slides. So the plot, this one, the plot by LIGO Virgo that you are showing does not include the observational bias. So it does not show the intrinsic population.
No.
Have you tried also to make some comparison of your model with the observed population after including the observational bias?
No. But I mean, the one bias I did mention, of course, these are, of course, completely overrepresented, the massive ones, right? And they're themselves interesting because it's not quite so clear where they come from. I mean, they might be dynamical, many of them, or other genres. But at this end, we also have, of course, observation.
Yeah, of course. Maybe we can discuss how
to
make the comparison, because it would be exciting, I think.
No, I think when we have started doing that, right? It's not, except that at the moment we were thinking that the number of sources is perhaps too small.
Yeah, super. Thank you.
Now, one slight disappointment is that LIGO is not quite as good as they were hoping for. So the sensitivity has only increased by, I think, 20% or so. But anyway, they have already found 61 more sources. So.
Okay. More questions from the floor? One there.
Thank you. How well do you actually know the absolute scale for the mass flow? For the envelope ejections. For example, if you take a long mass star like our sun, does one know when the mass loss due to envelope ejection becomes larger than the equivalent of the mass loss via energy? I mean, the normal mass loss via energy loss. Do you have models that precisely give the absolute timescales? I mean, you showed the intervals for the oscillations,
yes,
like 40 years or something.
Right.
But I mean, the absolute timescale for the whole evolution of the star is unknown.
We have, in the paper which is not published yet, we have tried to do that, but it's only first attempt because our mass loss rates are actually very high. We get in these during these thermal pulses, we get mass loss rate of 10⁻³ solar masses per year, which seems high compared to what observations tell us. But that's only during the thermal pulses, and the in between we have not taken into account yet. I mean, we do have a Reimers type stellar wind, but that's not very important.
Okay, Rob, question?
Philip, I was wondering what the influence of strong stellar rotation is on the picture you have painted throughout your talk, right? You might have meridional mixing.
I'm talking about big stars, and if big stars are single, then rotation is not very important.
But mostly they are not single, right?
Right.
And so,
but for the AGB stars, I mean, it's true. I mean, we have not. I mean, it's true. If you have a AGB star that merges with some companion, then you can have a rapidly rotating envelope. We have not looked into that. That's true. But you know, qualitatively, that will make it even more unstable. And it becomes bigger. You have centrifugal support. Yeah, I think it will be more unstable. Okay. And for the stars, at the core collapse, yes, these are all slow rotators. If you, by binary evolution, can form rapidly rotating ones, this picture is not valid. And of course, we don't think the supernovae are connected with normal neutrino-driven supernovae, but with some type of engine. Right, so that's not covered by this at all. But there's also, in that case, there is no longer the characteristic energy scale of 10⁻51 ergs, because that depends on the binding energy of the inner core. If you have an engine, the engine doesn't know about that. And so you can have much higher energies.
More questions from the floor? I don't see anything at the moment, and I don't see anything from the virtual audience. So if I may just add a question in a similar vein. I mean, you mentioned that the hydrodynamical simulations were beginning to produce supernovae now. And
I don't remember whether I said that they do produce supernovae. At the moment, the energies are not quite high enough to explain the observed
quite high enough.
But
okay, yes. My question was actually, I don't know whether it's the question of the what am I doing here? Yeah, okay. The chirps, but do you envisage maybe in the next few years that one could start to model the distribution of spins of these stellar remnants, the neutron stars, or even the magnetization of them? Because you seem to be very successful in doing this here, and presumably at some level whether or not you get a supernova does depend on the angular momentum. Is there a sort of coming together of the theory and the observations that could actually start to constrain the demographics of neutron star spins, for example?
I mean, one thing I didn't show, we make also predictions for the neutron star masses. So that's one observable we can already compare to the masses in double pulsars, for example. We are not making, do we make predictions about the spins? Not really.
Okay.
Not at this stage.
So that's just a too complex process. Is that just because of the actual difficulty in making the supernova happen?
No.
Or is it the pre-supernova evolution?
It's the pre-supernova evolution.
Okay. Okay.
For us, is more the problem, because then you need to really understand the angular momentum transport in the progenitor stars.
Right.
And I think that's where the uncertainties would be. So that's why we have not done it.
Right. Okay. I mean, is there any hope one day, you know, with more three-dimensional calculations?
I'll pass the question on to you.
I asked you a similar question, actually.
Is the answer.
Okay, good. Well,
Let's carry on.
there's one at the back. Let's have one final question. We're bang on time. Who was asking? Yes, right.
Thanks for the interesting talk. I also have a question related to rotation. So if I understand this general picture that you're presenting in this final slide correctly, that then you're actually saying that the rotation in the collapsing core does not make a significant difference to the outcome.
Right. We kind of know that observationally. Yeah. Okay. Continue.
Yeah. So my idea was that since one has rotation, then one has additional support by the centripetal force. Yeah. Right. So it's more difficult to launch an supernova neutrino-driven explosion for the one thing, and for the other thing, with rotation, not all of the final mass would collapse into a black hole. I mean, right?
You're absolutely right. If there were significant rotation in the core, that would be important. However, I would argue observation, we know that for the majority of stars, neutron stars, the rotation is unimportant at the time of core collapse. And this has to do with what you can deduce about the birth spin periods of pulsars, for example. They're not born at millisecond spin periods. They're born at tens or 100 milliseconds. And that means that's actually very slow. So if you then ask, I mean, what that means is that rotation support is not important at the level of the neutron star.
Okay, and then for the remnant masses,
but it's true. If binary evolution gives you rapidly rotating neutron star, then that would probably become a magnetar, and that may explain certain types of explosions. That again is not covered by what I'm discussing today. That's very interesting, but it's not covered by this.
Okay, and then the idea that even if you have a slowly rotating core, not all of the final mass collapses to form a black hole. But then the idea is that the amount of mass in the envelope is negligible, right, compared to the collapsing core? Or how come can one also neglect rotational effects in terms of the remnant mass?
You mean you're talking about fallback?
Just the idea that if you have a rotating collapsing star, not all of the final mass collapses, but part of it is used to form an accretion disk and
quite significant angular momentum.
Still, yeah. Okay. Okay, so the same line of argument there. Okay, thanks.
I mean, it's true that if you are further out, long way out, and if you have a solid body rotating core, yeah, that could form, in principle, a disk-like structure, and that has been hypothesized that some neutron stars have some disks around them. There's some observational counterparts, possible counterparts. So that's possible, but I don't think that will affect my picture. Right?
Okay, well, we've had quite a discussion, and before we thank Philip again, I have an announcement to make. So it just remains for me to thank you very much again, Philip. We really much appreciate your wisdom and insight in all this, in this what I have to say is surprisingly a very rapidly developing field. When I first came here, I thought, well, stars, we know everything. Now we know what we don't understand. And thanks to you, we actually can see a lot more about what's actually going on. And so thank you very much again for telling us all about that.